either my log block is, 2/3 full, or until 30 milliseconds have passed, whichever one comes first. A short extra period of time. And there may be, if I have a lot of transactions going on, and busy systems, I have a lot of transactions going on. I'll wait maybe that 30 milliseconds or whatever it is, and maybe I'll have 5 different transactions with commit records that are inside that block, or maybe in consecutive blocks, since maybe a new block got started. I will do one force that takes care of all of them, one force to rule them all. All of them get written out. By waiting that maybe 30 milliseconds or whatever it is in a busy system, I've taken care of 5 transactions with one blow. Brave little Taylor. I've written 5 transactions with one flush, one force. Isn't that great? Now you would say, but what if you don't have a busy system? Well, right. If I don't have a busy system, then I'll just be waiting the 30 milliseconds. I'll force things out. It's not a busy system. I'm worried about throughput. Doing 5 transactions at once matters when I have a really busy system, or 5 or 10 or however many it is. If I have a very unbusy system, then I'll delay a little bit. But what the heck? It's not a big deal. If I'm not going to 30 milliseconds set your favorite constant. How much are you willing to wait to try to write more things out together? And it's 30 milliseconds from the first thing that caused me to set my timer, not 30 milliseconds from the last thing. And that's called group commit, because I'm committing a whole bunch of transactions at once. It's called boxcaring. It's like containerized cargo or boxcar on a railroad. I'm having a bunch of transactions that go out together. A neat trick. And when the commit record has been written on behalf of one or more transactions, has been forced, then the commit command that came from an application returns. And at that point, I've completed all the obligations that I have. After I send my message back on the commit, I write an end record to the log, and the transaction is committed. Nothing more to do on behalf of this transaction. So how does crash recovery work? Here's the big picture, and we'll go into detail, but there are some slides where I say, I want to ask you for the full detail on the exam. So basically, if there's a crash, then remember what you have. You have your checkpoint record, you have the current state of the database, you have the current state of the log. And so you can start from the most recent checkpoint, which again, you have this safe place and you know where it is, unlike my wife and me who forget our safe places. You know where the safe place is. You start, you know where the most recent checkpoint record is. Okay? And you're going to go through 3 phases: analysis, redo, and undo, that are in the Ares algorithm. So you've got the crash, and basically what you're going to be able to do is you're going to go through the blue, the red, and the green to be able to recover using the most recent checkpoint. Here's basically how things work. You're going to go ahead and you have the end checkpoint record. So you have information which it's still fuzzy. More work could have happened after, but that's all to the good. Idempotency allows you to make everything okay, even if more work happened. And you construct all the dirty page table and the transaction table as of the time that you started the checkpoint. Again, it's fuzzy. Things may have gone forward. And basically, from that checkpoint record, you have the LSN of the checkpoint record, that end checkpoint record. So you have the LSN of it. You know what the LSN is. You have the log after that checkpoint. What you're going to do is you're going to scan the log going forward from that end checkpoint record, which itself is a log record in the log with its own LSN. And when you hit an end record, that means I don't have to worry about the transaction. Everything involving it has been taken care of. I can remove it from the transaction table. And basically, if I go ahead and find other records like that are there, for example, I will add that transaction to the transaction table. I'll set the last LSN to be that LSN, and I will change the transaction record when I see a commit to say that the status for it is committed. And in particular, and there can be all sorts of records, commit rollback records, you know, and so on, as well as update records. But here's the important thing about updates. If there's an update record, then if the page that was updated, which I have in the update record, I know what the page ID is. If that page is not in the dirty page table, that means I dirtied that page after the checkpoint. Put that page into the dirty page table and set its rec LSN to be the LSN of the record that dirtied it, that we just found, the first thing that dirtied it. So, okay. So that's actually the analysis phase, and that's pretty easy. It gets a little bit harder from there. The redo isn't hard, the undo is amusing. General idea of the redo? Everything that's in the log on behalf of a transaction where I have a log record, I'm going to redo what that record said. Everything that's in the log since that checkpoint that involves an update where there's something that was an update, insert update or delete, I'm going to do whatever it is to redo it. Now, the stuff that's a little tricky here is there could be things that I'm redoing for transactions that later on I discover were rolled back. That's okay, I'm still going to do everything. I'm going to just be playing back the log, rolling forward everything that's in the log, redoing everything that the log records tell me to do. Okay, so I'm going to replay all the updates, and I'm also going to be redoing the compensation log records. The compensation log records tell me what it is that I undid and what the undo value is. And again, all these things are idempotent. So basically, I'm going to scan forward, and I'm going to do it based on the log record that has the smallest rec LSN that's in the dirty page table. And for each CLR or update record, I will redo the action with some exceptions. If the affected page is not in the dirty page table, then I don't have to bother. That all got taken care of. So if it's not a dirty page, I don't have to apply it. And if, basically, I have a situation where the affected page is in the dirty page table, but the thing is that the rec LSN is greater than the LSN, or and there shouldn't be a dot there, or the page LSN in the database is greater than the LSN, there's no point in bothering to do it, because basically the thing already got taken care of inside the database, so there's no point in bothering. Okay, so I could do it, but there's no point in bothering, because you know the changes have already taken place. And to actually redo an action, you do the logged action. You redo whatever the new value is. And you set the page LSN, right, that exists for that page to the LSN, which is, again, the latest change that corresponds to that page. And you don't do, when you do the redo, there is no additional logging that takes place during the redo. So basically what it comes down to is you're redoing everything that's there unless you discover based on the LSNs that there's no point in doing it, it's already been taken care of. And that's what the redo does. And it includes redoing the CLR stuff, because you need to make sure everything for a rollback transaction gets rolled back. And again, undoing twice is okay, it's unimportant. Now here's the funny part. And again, I'll give you the top level. Now that we've redone everything that needed to be redone, including taking care of everything that was committed, what's left? The transactions that rolled back, or the transactions that were active at the time that the crash occurred. All of that stuff has to be undone. If 'twere undone, 'twere best were undone well. So basically, what you're going to do is you're going to figure out what the loser transactions are. Who are the loser transactions? The transactions that you discovered that rolled back while you were rolling forward, and the transactions that were still active based on the transaction table at the time of the crash. You went through the entire log. Anything that committed has been completed. Anything that was rolled back is a loser. You know what its last LSN is. Okay? How do you know what its last LSN is? You've been keeping track. You've been keeping track of all the LSNs for each individual transaction inside the transaction table. So you know what the last LSN was, because as we described during redo, basically you're going ahead and you're keeping track of the LSN for each individual transaction. And so here's what you're going to do, both for every transaction that rolled back and for every transaction that was active at the time of the crash. You're going to know what its last LSN is. These are the losers. Okay? And basically, you go ahead and effectively, and I can go through the detail, but let me tell you what the general idea is. For every transaction that's supposed to be undone, you undo it. Now, the amusing part is that basically, you could have a situation where the LSN, where what you do is you find a log record that's a CLR, and there are two possibilities. Either its undo next LSN is null or it isn't. Remember, the undo next LSN for a CLR tells you about things that are chained together that you're supposed to undo. Remember, when you undo, you go backwards. And there could be a crash in the middle of your undoing a transaction. Again, this is the really annoying part to get right. There could be a crash while you're undoing a transaction. So what do? You know, basically, you have a log sequence number that's a CLSR. You don't undo the undo, but you have to follow through the chain of the other work that needs to be undone on behalf of this transaction. Fortunately, in the CLR, you've got the undo next CLSR. Undo next LSN, rather. If undo next LSN is null, it means there's no chain. You've gone through the entire chain. Everything that needed to be undone has already been undone. No more work to do. And if you have a case where the value is not equal to null, then you're going to have to undo that record as well and follow the chain. And that's what this stuff is going to be doing effectively, and I'm going to describe it more easily than what's on this slide. You undo everything that needs to be undone, and you have an optimization using the CLRs that allow you to figure out which undos have already been taken care of and which ones haven't. So you undo the things that you need to be able to take care of. And in a situation where the LSN is an update, then the update described what the old value was. You go ahead and you undo the update, and you write a CLR that corresponds to it. During undo, you write CLRs that help you understand what needs to be taken care of, and the undo and the CLR is going to again give you the value of prev LSN that you also write as part of the CLR. So again, you can follow a shorter chain if there's a crash during the undo. And basically, you undo everything you need to undo. And there's a sequential order, which you undo following, you know, the largest value in the undo. So you're effectively undoing going backwards through the log with some optimization where you don't have to undo things that don't need to be undone. But you're going backwards through the part of the log where work needs to be done. And you just undo everything on behalf of the transaction that rolled back. So this is a little more complicated. It's an optimization, but it really is go back through the log and undo everything that needs to be undone. Undo everything on behalf of the transaction that rolled back or was active at the time of the crash. And again, there's a little more optimization there. And I'm not going to spend a whole lot of time on this, but you can see how this works on pages 593 to 595 of the thing. And basically, you will basically be able to keep track. I'm not going to go through the detail, but basically, we have a situation in which you could have a rollback and abort of transaction T1, and you're going to have things that end up getting written to the log that corresponds to LSN, the LSN for the CLR, and if T1 ends, everything's cool. If you end up having, T3 writing P1 and T2 writing P5, and you end up having the restart, then you're gonna have to basically go through and handle what you need to be able to do on behalf of those things. So basically, you're gonna undo, the T2's rights. You're gonna undo T3 right. If there's a crash, before you undid T2's last right, then you're still going to be able to do a restart, and you're going to be able to follow the links to be able to undo. And again, it's idempotent. You'll undo everything that you need to undo. And again, because it's idempotent, everything needs to be okay. And again, there's more detail on that, which I'm being sloppy about, but I'm just not going to bother going through the full detail on this. Take my word for it, it works, and it's not that hard to figure out. Very, very quickly. Analysis, you get the transaction table, you get the dirty page table using the master, using this master record, which tells you about the most recent checkpoint. You redo everything, including perhaps on behalf of transactions that need to be undone. You undo everything on behalf of transactions that were either rolled back or that were active at the time of the crash. And so there are things that require more analysis. What happens if the system crashes during analysis, during redo, during undo? All this stuff works. Again, the detailed proof of that, there's some stuff about it in the textbook. I'm not going to go through it, but if you have questions about it, ask me. Point is, again, all this stuff is going to end up being idempotent. Analysis doesn't do a big deal. Redo does some stuff, but again, redo never hurts. And the crash during undo, this is why we have the CLR records to help make all this stuff work. How do you limit the amount of work that you need to do in redo? By taking checkpoints more often, and also by writing out your dirty pages more frequently. I mean, dirty pages, you can leave dirty pages around for a long time. They're big buffer pools, but you don't want to do that. This will be too much work to be done on that very behalf. So you may flush asynchronously in the background, and so on. How do you manage limit the amount of work in undo? By not having really long running transactions. If you have a lot of really big transactions with a lot of work, then the amount you have to undo would end up being more. Sometimes you play with things via save points and nested transactions, which I haven't gone into, that helps limit that. So now we have the overall summary, which is good because I only have about 5 minutes left. The stuff that we've spent the last 2.5 lectures or so talking about guarantees atomicity and durability, as opposed to the stuff on concurrency control that handles isolation and consistency. Write-ahead log operating with steal no force allows you to be able to, get good results without sacrificing correctness. You may write out a page that has stuff that isn't real on it. That's what steal is, but you'll be able to undo that using write-ahead log. And not forcing is okay. You do have to force when you have a commit record. You don't have to force when you have a rollback record. The LSNs chain together log records, and they're ever increasing. And there are also the special log records that we've talked about. Using these funny, page LSN and things allow us to figure out about page LSN versus flushed LSN to be able to do write-ahead log. Checkpointing, fulfilling my obligation to you. Takes care of not having to use the log going back to the beginning of time. And it's fuzzy checkpointing, and it's really important. I don't want to stop processing while I get a consistent, don't want to have a lock on anything going on while I get a consistent image of the dirty page table and of the transaction table. I don't want to have to bother stopping work from going on while I'm making a copy of that stuff. There are 3 phases: analysis, redo, and undo. Analysis, get the information that describes this fuzzy picture of the dirty pages and the transactions. Redo, take everything that existed from the beginning of the start of the checkpoint, not the end of the checkpoint. Everything, because it is fuzzy. Take everything from the beginning and redo everything that's in the log as of when the checkpoint started. Undo, go backwards through everything that is in the log to undo things there again. And there's some clever, hard to understand optimizations that are going on there that mean you don't have to read the entire log, but only the things in the log that end up being relevant. When you do the undo, you write CLRs, compensation log records, which again help you figure out what's going on after a crash. You never undo the undo. What's the point? The undos are really supposed to be there. But the undos help you follow chains more easily to figure out what else needs to be undone. So you write the CLRs to do that. And the redo, basically repeats history, and important that it's idempotent. There are clever games that can be played with respect to that, which, for example, if you know what log sequence numbers have been applied to a page, then you don't have to apply them a second time. If you know that I've applied everything up to log record 2006, and I have a redo that has 1940 in it, then I don't have to redo the 1940 because I know that I'm okay through 2006 in that page. Again, there are clever games that can be played. And now this is a slide that I also added, which is a POTUS slide. There's a lot of work that's been done on recovery since that goes beyond what's described in the textbook. But what we described is complicated enough. All these, again, if somebody wants to talk to me about them, let me know, and I'll be happy to talk about any or all. These are all three very interesting modern papers. The oldest of them goes back, 2-3 years. There was work at CMU. Pavlo is a professor there. Joy Alvaraj was a student of his who's currently a professor at Georgia Tech. And they did work in the context of non-volatile memory, which I've already mentioned to you before. New devices lead to new algorithms. So they created something which is called right behind logging, because the disk is replaced by a non-volatile memory. And so you still want to be able to have a log, but you write to your durable database and then you write to the log. It's, again, right behind logging instead of right ahead logging. And it's a really clever, nice kind of paper. They've done other things having to do with non-volatile memory since then, cooperative relationship with Intel, among other things. There's work that was done at Amazon. I'm going to point you to an earlier Amazon paper in some of the later lectures, but this is a more recent one that, again, talks about Amazon Aurora. What is Aurora? What Amazon did, which is really clever, is they took open source database systems, in particular MySQL and PostgreSQL, and they said, there are interfaces to these systems. Let's maintain those interfaces approximately. But let's put a totally different lower half of the database system in that takes advantage of how we deal with storage and replication and so on. MySQL allows you to put in whatever lower level database engine you want. PostgreSQL isn't as friendly that way, but they did the same thing with PostgreSQL. So they're emphasizing the MySQL version of this. So they have a totally different lower level underneath MySQL that deals with storage and concurrency control and recovery and all the stuff that we've been talking about. And it's set up to have an incredible amount of replication. They pay the price, they have fast messaging, they pay the price of doing the replication. You know why? Failure is not an option that they want to consider. They want everybody to move MySQL to running on Amazon, and basically, even if you have an availability region, the availability region failing, and one more node failing, Amazon Aurora will still keep on working. They will pay a small response time penalty for doing that. It's something where you will be operating with basically 6 copies of the data and 3 availability regions with 2 copies of it, sometimes 7. But basically, why don't they want failures? Telling users how to deal with failures, it's complicated, expensive, operators get things wrong, it's incredibly ugly. It's terrible publicity when it ends up happening. It makes the customers unhappy, which is an economic burden. Basically, operators, there was a survey that this guy, Jim Gray, that I keep mentioning, did at Tandem, and on the order of, was it somewhere between 25 and 50%. Sorry, it's been a while. I forget whether it was 1 quarter or 1.5. Of the errors that existed on Tandem systems, which were supposedly nonstop, or at least that was the trademark for Tandem. That percentage, let's call it 25%, but I think it was more, of the errors were caused by operator mistakes. operators have a hard time dealing with things going wrong, because things don't go wrong very often. And so coping with them ends up being something that they haven't learned. If you only have fire drills when there's a fire, you'll get burnt. And explaining how to deal with some of the issues ends up being really hard. So basically they're saying, let's make sure we don't have problems. By paying a price, a small price, not as big as it used to be, by having extra latency. But we'll work well. We'll make operations so cheap that you won't even have to have an operator. It'll just work. That's a savings too. And then there's work for something called Fine Line that was done around, or initiated around the same time as some of the work in Amazon, where again, they did work, a lot of the work that they've done on original parts of this is called instant recovery. The idea is that you don't have to pay a price worth mentioning to recover. Recovering is essentially instantaneous. You get something like the same thing with the Amazon. So the emphasis here, and I'm out of time, is that what you've seen on Recovery with Arrays is still really important work, but the work keeps going on and changing. Clever algorithms, different network speeds, differences in cost, all of these different variations, different devices, all these different things end up going on. We are now done with the transaction processing. I will be spending the next 2 or 3 lectures on this parallel and distributed database. I'll put both of those lectures up. As I mentioned, we'll see whether we get to things like more about LSM trees and about the spatial data, but although parallel and distributed will be on the final, the work having to do with these spatial data and additional stuff in LSM will not be on the final.